Logarithms are exponents. We now define one of the most important functions in mathematics, the logarithmic function. So we say the expression y equals the log base b of x is equivalent to the expression x equals b to the y power. B has to be a positive number and b cannot be equal to 1. So again, in this expression, b is the base of the exponential function. And here we say b is the base of the logarithmic function. So another way to think about logarithms when you see an expression like this is y is the number we raise b to in order to get x. So some examples, just to help us with a fundamental understanding here. We know that 8 is 2 to the third power. So I can say that 3 is the power that we raise the number 2 to get 8, right? 3 is the power of 2 to get 8. We also know 5 to the second power is 25. So the power of 5 to get 25 is 2. 0.1 is 10 to the negative 1. So the power of 10 to get 0.1 is negative 1. So when a number is equal to a logarithm, that number is just the exponent of the base to get the number you see here. And this is why we say logarithms are just exponents, right? So let's consider if I wrote down logarithm base 3 of 81, and I asked you, what is this equal to? Well, this is the power of 3 to get 81. So what is the power of 3 to get 81? You could figure this out. You know that 3 to the first power is 3, 3 to the second power is 9, 3 to the third power is 27, and 3 to the fourth power is 81. So the power of 3 to get 81 is 4. So the answer here would be 4. So we can use this very basic definition to help us solve equations with logarithms. So in this particular example, we have logarithm base 3 of x is equal to negative 2. Now, another way to help you interpret a logarithm is by drawing a little diagram. So I'm going to start at the base, and I'm going to draw an arrow over to the other side here, and then an arrow back over to here. And so the meaning of this expression, or this equation, is 3 raised to the negative 2 power is equal to x. Okay? So what would x have to be then? Well, x is 3 to the negative 2. But we know that 3 to the negative 2 is 1 divided by 3 to the positive 2. And that's equal to 1/9. So x would have to be equal to 1/9. Here's another one. Suppose we have log base x of 4 is equal to 3. So again, I'm going to start with the base here, draw an arrow here, and draw an arrow back here. And so this equation is equivalent to x to the third power is equal to 4. Now, what would x have to be if this were the case? Well, if I have x to the third equals 4, I can get rid of the cube by simply taking the cube root of both sides. And the cube root of x cubed would simply be x, and then we would get the cube root of 4. So x would have to be equal to the cube root of 4. In the next example, again, very similar, we have log base 8 of 4 is equal to x. So this is equivalent to 8 raised to the x power is equal to 4. All right, but how do we solve for x, right? Like, what is the number x that makes this true? So for this one, we're going to employ a little technique here. I want you to remember that 8 is 2 to the third power. So if I have 8 to the x, it's just going to be 2 to the third power raised to the x. And 4, of course, is 2 to the second power. So what I'm doing here is I'm finding a common base between these two numbers. So 8 and 4 have a common base of 2 because they both can be expressed as powers of 2. Now on the left-hand side, this becomes 2 to the 3 times x. And on the right-hand side, we just have 2 to the second power. So all I'm doing here is multiplying these together. That's actually a property of exponents. And now, if 2 to the 3x is equal to 2 to the second power, then 3x must be the same as 2. So we can get rid of the 2, the base on both sides, and get 3x is equal to 2, which means x would have to be equal to 2/3. Oops. There we go. Next, let's talk about how to graph y equals log base 2 of x. So let's remind ourselves that y equals log base 2 of x. If I change the format, that's going to be the same as 2 to the y is equal to x. And I want you to notice that that is the inverse of y equals 2 to the power x, right? So if I just switch x and y here, I get y equals 2 to the x. Now, the reason I'm bringing this up is because we just talked about how to graph y equals 2 to the x. All we would need to do here is plug in a few points. So those would be the x and y coordinates for these particular points. And then since this is the inverse of that, this graph would simply have the same coordinates but just flipped around, right? And these points are on this graph, but that is the same as our original. So if we graph these together, we get this. So y equals 2 to the x is our very common exponential function. And y equals log base 2 of x, or x equals 2 to the y, either way, same thing, gives us this graph. So logarithms are simply the inverse of exponential functions. And in fact, more generally, we can say that y equals log base b of x and y equals b to the power of x. These two functions are inverses of each other. Okay, now they do, of course, have to have the same base to be inverses of each other. But in general, this is true. And finally, we have two special identities because of the fact that exponential functions and logarithmic functions are inverses. We have one identity that says if you take the number b and you raise it to the power log base b of x, you simply get x. So basically what happens here is these cancel out. Likewise, if you have the log base b of b to the x, you also get x. And so these simply cancel each other out. So for example here, if I want to simplify log base 2 of 8, one way I can do this is I can just remind myself that 8 is the same as 2 to the third. And so now since I have log base 2 of 2 to the third power, these cancel out and we just get 3. Same thing for part B. Here we have log base 10 of 10,000. Let's rewrite 10,000 as 10 to the fourth power. And see, now I have log base 10 of 10 to the fourth power. And so log base 10 of 10 cancels out, and we just get 4. Part C, we have log base b of b. Let's keep in mind that b is the same as b to the 1. So once again here, I can cancel out log base b of b, and we just get 1 left over. Okay, next one, part D here, log base b of 1. This is kind of a special case, but remember that 1 can always be expressed as any number to the 0 power, right? So b to the 0 is 1. And then once I do that, I can cancel these out, and we just get 0. And finally, we have log base 4 of log base 5 of 5. So now to figure this out, let's just start on the inside, and let's say, what is log base 5 of 5? Well, keep in mind that 5 is the same as 5 to the 1, and these cancel out, and we just get 1 here, okay? So this is equivalent to 1. So then what we have is log base 4 of 1. But we know that 1 can be expressed as 4 to the 0, right? Could actually be expressed as any number to the 0. Now, why am I choosing 4? Because if I pick 4, these cancel out, and we just get this number here. So this is equal to 0. Now, we have some other properties of logarithms coming up here, but this is just to serve as a brief introduction to logarithms. And that concludes this video lesson.